So there are three more types of simple machines we need to go over: the inclined plane, the wedge, and the screw. So, little recap: mechanical advantage is either the ratio, the magnitude of the forces, or it's the ratio, the magnitude, or the distances that the forces move the objects themselves. Ideal mechanical advantage: if you're ever given two distances, take your effort distance divided by your resistance, or your input divided by your output. Divide those two, you've got ideal mechanical advantage. If you ever have two forces, take your resistance force divided by your effort force, and you've got actual mechanical advantage. So the force of your output over the force of your input. So let's talk about an inclined plane. We started off our videos looking at this example, and we'll go ahead and we'll continue it here. So we've got inclined plane. Ideal mechanical advantage is the distance of the effort over distance of the resistance. So we look at this slope right here. The effort, if I'm going to push it up the slope, that distance there is that hypotenuse of that right triangle, or 15 feet. What's the resistance? The resistance, the total distance, or the horizontal distance that is moving, or vertical distance that's moving, is just 4 feet. So I've got 15 divided by 4. I've got ideal mechanical advantage of 3.821. For every 3.8 feet this way, it goes up 1 foot that way. Actual mechanical advantage, same thing that we've looked at before. If you've got two forces, you divide them. It takes me 20 pounds of force to move this 50-pound object up this hill. So the actual mechanical advantage is the 50 pounds of resistance over the 20 pounds of effort. I've got a 2.5 actual mechanical advantage, greater than 1, so it takes me less effort than resistance that's there. So efficiency, AMA over IMA, calculate those from the previous slides. We have a 68% efficiency. Next type of simple machine we're looking at is the wedge. It's an inclined plane. You're going and you're moving this distance from that to that is a distance itself, so all we're looking at is inclined planes again. We've got the wedge, the IMA, again, distance over distance. Distance of effort, distance of resistance. So when we look at that, we've got the effort is being applied is that L that's there. So we're trying to push this starting point on that wood from the previous slide. We want to push it up to there. So we're pushing that wood from here to there. So that 10, the resistance has got to move that 3. So when we're done, the wood is all together splitting that 3 inches apart. So we take that 10 divided by that 3. We've got a 3.321 ideal mechanical advantage. Look at actual mechanical advantage, force of resistance over force effort. So the resistance is what's in that wood, and we'll calculate these type of forces later in the year, but it's got a resistance force of 700 pounds that would be given to us. We're trying to find 250 pounds of effort, so the actual mechanical advantage is 2.8. So the actual mechanical advantage, 2.8. Go ahead and split that. So by using a wedge, it takes less force to split something because 250 input gives us 700 output that's there. So efficiency, AMA over IMA, divide those two out, we get efficiency of 84%. The last simple machine we want to look at is the screw. All the screw is an inclined plane. We are changing and we want to get from here to there. So we've got an effort distance, we've got a resistance distance that's there. They just got some different terminology to be able to work with. Couple things that you want to think about when you're trying to look at the mechanical advantage of a screw itself is what kind of tool are you going to use to put that screw in. So what is the distance of that screwdriver? Smaller screwdriver is a smaller distance. We should know what that means. A larger screwdriver, a longer screwdriver is a longer distance. We should know what that proportion will help us do. We've got the pitch. The pitch here is the distance between those threads. So for every rotation of the screw, we're going to go in that amount into the wood or metal or whatever else we're going into. So if we're looking at this thread information, screws are read as 1/2 13 NC. Diameter being 1/2 means the diameter of the screw itself. The 13 is how many of these threads are per inch, and NC is the type of description. Is it coarse or is it fine? So depending on what type of material you want to use. So if there's 13 threads per inch, then the pitch is 1/13 of an inch. So how far will this screw with 13 threads per inch move? If we turn it one rotation, it'll move that 1/13 of an inch. If you take a screwdriver or a wrench and you move that one rotation around, you're going to go into that object 1/13 of an inch itself. So what is IMA? IMA is distance effort, distance resistance. Effort is rotation of the arm or the wrench that you're using. So that's their circumference. The resistance is the pitch, how far it's actually going to go and travel in that rotation. So your effort, input, output. So the IMA is your circumference of that wrench that you're going to use, 2 pi r over the pitch itself. So if we want to calculate this, we got an 8-inch long wrench. So take your 8-inch long wrench. That means the radius is 8. Think of moving that in a circle with that fulcrum point in the middle. So therefore you got a radius of 8, a diameter of 16 is being applied to this screw. Well, this screw has got threads per inch of 20, so therefore the pitch is 1/20. So we've got 2 pi 8 over 1/20. When you divide by a fraction, you flip it over and multiply. So we've got an ideal mechanical advantage of about 1,000. Calculate the AMA. Well, the AMA that we've got here, when we're trying to create it, is force over force. So we're going to apply 35 pounds of force and try to move into a force that's fighting against us of 1,200. So resistance over effort gives us an AMA of 34:1. Again, large mechanical advantage. That means it takes us a lot less effort to try to go into that board. Even though it might seem hard to screw something in there, it's a lot less effort because of that mechanical advantage and that simple machine working for us to be able to move into that object. So the efficiency, well, what do we expect that efficiency to be? We should expect it to be kind of small. If you've ever tried to take a screw without a drill and screw that into a board itself, it takes a lot of work to do and you don't feel like you're getting that far. So the efficiency, the energy you're putting in, is not equal to the energy that's getting out or how much is being created when you're trying to do that.